Okay, wait a minute or two for everyone to populate, and then we'll get started here. Okay, here we go. So, welcome to e-learning, everyone. We are going to pick up exactly where we left off with was Pythagorean theorem in 3 dimensions. So this class was meant to be, since this was a brand new thing, not Pythagorean theorem, but the Pythagorean theorem in 3D. This class was meant to be a double class, so you got 2 doses of this. Because it is somewhat of a challenging thing. Oh, by the way, the worksheet that I gave you before, make sure you turn that in on Teams. And then lastly, there was one on a hexagonal pyramid that I keep telling myself every year, take that one off the worksheet or put it on the homework saying skip that one, and I always forget to do it. So for those of you that tried to do the hexagonal pyramid, yeah, that one was an impossible one to do with your given knowledge. I will teach you how to do that in high school. All right, here is your homework tonight. It's already posted right now. You can already see it. It's just basically a second worksheet on the same material. So it's not that I'm going to speed through this. However, I am giving it to you a second time. Please chime in if you have any questions. Just so you know, I got to teach the whole day. So if you send me chats like Landon Holler just sent me a chat, sometimes I can answer it immediately, but most of the time I'm actually teaching, so I can't actually answer your chats very quickly. But I will promise you, I will answer all your chats as soon as possible, and I will have my computer on until 8 p.m. at night every day for the next 2 weeks. So if you have any needs or requirements, or you want something answered or whatever, it absolutely in the evening, you'll get a very prompt response unless I'm having a Zoom tutoring session with someone. Okay, here we go. So Pythagorean theorem in 3D. This is just basically class number 2. I'm going to use the same slides. I'm going to use the same material. So sometimes hearing things a second time, I mean literally hearing things a second time, is a good thing because it kind of sinks in. So as you see the slide, try to be thinking ahead of what I'm trying to say and see if it matches your prediction of what I would say. We're doing pyramids, cones, and rectangular prisms. The rectangular prism is the most challenging one. It's the largest thing that can fit inside of a box. And we're talking about lengthwise. You could get into some arguments of, what if the shape was weird or curved or something like that. We're just talking about, I don't know, imagine a baseball bat. What kind of box? What's the smallest box that a baseball bat or a pool cube could fit inside? That's the basic idea. And what you're really doing is you're measuring the diagonal length of a rectangular prism. In other words, from the top of one corner of the box to the opposite bottom corner, what is that distance? We started off the last time we met on Monday talking about this new concept of something called slant height. Now, there are slant heights for both pyramids and for cones, but the idea of slant height is the distance on the outside of the shape to the vertex. So we already have this idea or concept of height. Height is the perpendicular distance. That's why there's a right angle. The perpendicular distance between the base and the vertex of a pyramid. Same thing for a cone. Slant height is that, well, it's sort of the same concept. It's a perpendicular distance, but it's a distance along the outside edge to the vertex. So you get this shape in red right here. And the obvious thing that you do once you have this shape is you connect the 2 red segments there, and it makes a right angle. Therefore, to do the calculations of both height and slant height, we can see that we can actually use the Pythagorean theorem to get some of those answers. Lastly, this. Yes, I will only be giving you square pyramids for all of these problems. So if it's a square pyramid, that means for the base, all the sides of the square, the bottom of the pyramid, unless it's turned on its side, are the same measurements. In other words, if it's a square, then the left side equals the right side equals the back side, so forth and so on. Okay. So we know that from our study and our quiz on Pythagorean theorem that a squared plus b squared equals c squared. So you will be given some distance. And yes, this is the same one that we saw on Monday. So it is a square. Notice I didn't say up here, and this is my fault, it should say calculate the slant height of the square pyramid. So if we calculate the slant height of this square pyramid, we're talking about, let me get something I'll draw here. We're talking about this distance right here. So in red, oh, that's a horrible line. But we're talking about that distance right there, that green dotted line right there. That would be the slant height. Okay, so how do we do that? Well, we're going to use the Pythagorean theorem in order to do that. All right, so using the Pythagorean theorem, we know that a squared plus b squared, or the square of the legs of a right triangle, or the sum of the square of the legs of a right triangle is equal to the square of the hypotenuse. And for those of you that I said the other day, I was like, hey, you guys have some challenges with right triangles. Remember, the side that is opposite the right angle is the hypotenuse. So C ends up being the hypotenuse of our triangle, right, that we need to calculate. One of the legs, it doesn't matter whether you label it A or B, is 3. Where am I getting that from? Well, I'm getting that from the fact that this side, it's a square triangle or square pyramid. So that if this side is 6, then if we're going from the middle of the base, then half of that would be 3. So that's where that 3 comes from. And obviously the height there, the normal height from the base to the vertex is 10. So we throw those two values in for the two legs of the right triangle, 10 and 3, and then we just go to town on the Pythagorean theorem. Remember the Pythagorean theorem, a squared plus b squared equals c squared, 10 squared is 100, 3 squared is 9, 100 plus 9 is 109, and now we have a problem. Everyone grabs for their calculator, but remember, we could also do this without a calculator. The square root of 109, not a perfect square, so not in that box 1 at the start of the chapter. Well, it's got to be somewhere between two perfect squares, and the two perfect squares that squeeze it, somebody chime in real quick. What two perfect squares squeeze 109? Anybody? There are 12 people here. Somebody talk besides me. Waiting on you guys.
121 and 100.
Thank you. So 100 is slightly smaller. So the square root of 100 would be slightly smaller than 109. And the square root of 121 would be slightly bigger. Now, this is what everyone every single person in the class did this. Where the mistakes came was the next step. Well, the square root of 100 is 10. Saw this also. The square root of 121 is 11. So we know it's somewhere between 10 and 11. This is the part where people started messing up. 100 is 9 away from 109. And 109 is what? 12 away? Is that right? Yeah, 12 away from 121. So notice 109 is just slightly closer to 100 than it is to 121. Now notice if these two numbers were exactly the same, it would be dead smack in the middle. If it was dead smack in the middle, it would be 10.5 would be the answer. But we're not exactly in the middle. We're slightly closer to 100. So maybe not 10.5, but maybe 10.4 or 10.3 would be our approximate answer. If you actually do 109 on your calculator, I'm sure some of you did, you get 10.4. Okay, that is the process of estimation that you have to be able to do. Now, if you're lucky, I'm going to erase everything I just did. If you're lucky, the instructions say round to the nearest whole number. And if you round to the nearest whole number, then it would be 10. But if we round to the nearest tenth, which is what it typically says, it's about 10.4. I left off units here. There are no units here, so we would put the word 10.4 units. Okay, so there's your first calculation for slant height. Questions? All right. Now, we don't always know the two legs. Sometimes they will be given the hypotenuse. This one's not. But this is a previous one that we did. It's the same one we did on Monday. So once again, notice that this side right here is 16. So this side right here would be half of a side, only if it's a square triangle, and it is. So that side would be 8. Okay. So I've got legs of 24. Notice this arrow is pointing not to the hypotenuse. Remember, the hypotenuse is the side that is opposite the right angle. Okay, so that would be your C that the red arrow is pointing to. But in this case, we have two legs of 24 and 8. All right, big numbers, no big deal. We got a calculator. 24 squared is 576. 8 squared is 64. We add those together, and then we take the square root of both of those. Now, this is clearly a calculator problem right here because we don't have that one memorized. I said that we need the first 16 perfect squares, and that one's not one of them. By my calculator, I get about 25.3. Questions? Okay. All right, moving on. So here's one where we are not given both legs. We are given a leg and we're given a hypotenuse. Now, how do I know it's the hypotenuse? Remember, the side that is opposite the right angle is your hypotenuse. The side that is opposite the right angle is your hypotenuse. I will almost always draw this little red arrow whenever I do these problems, just so I don't mess it up. All right, I can ask this question two ways. I can say, what is the length of the unknown side of the green triangle? Or I could say, what is the one of the lengths of the base of the pyramid here? And I'll show you both of those answers here. So 42 is one leg. The other leg is unknown. We'll call it b squared. So 42 squared plus b squared equals 45 squared. So that's my setup. Boy, do I need a calculator now. We square 42, we square 45. Stop me if I'm going too quick. We square both of those numbers, and now we just use a little bit of algebra. We get rid of the 1764 first. It's attached by addition, so we subtract 1764 from both sides. We get that number. Ooh, we have that number on our list, right? We could squeeze that one. We could do this one by hand. Well, let's see. Doing that one by hand, that would be what, 256? Do we have a number bigger than 250? Oh, no, we don't. So actually, we can't do that one by hand. So, I mean, we're in the square root of 256 is what, 16? So we're just at our limit of perfect. But I do know it's between 16 and 17, and it's awfully close to 256. So even though I don't have all my perfect squares memorized, I know that 16 is 256. So, I mean, I could guess 16.1 or 16.2. But yeah, with a calculator, you can get to that one. And it turns out the square root of 261 is 16.2. All right. I will try to be very, not accurate, but very, it will be easy to understand how many decimal places I want you to round something to. All right. Anyone having a question? Anyone have any questions? Slant height. Now, technically there, we weren't calculating slant height. The slant height was 45. We were calculating this B distance, which is 16. Oh, by the way, if this distance is 16 or approximately 16, then the side of the pyramid will be about 32, okay? All right. Moving on. So there's your pyramid. Let's do it with a cone. So a cone, well, nothing really changes. I mean, obviously it's a different shape, but this idea of slant height would be the distance along the outside perpendicular from the base to the vertex. Okay. So even though there isn't, I mean, in this one particular picture, even though there isn't a right angle right here, that would be a right angle. Okay. All right. So those are your parts, your two heights as indicated on this problem. Let's connect those two and notice, once again, we get a right triangle. So we can use Pythagorean theorem to help us calculate either height or slant height of the cone. If those of you that can't picture the right triangle, well, there it is below. So what I'm claiming is that this right here, this side right here would be the height, and this side right here would be the slant height. Okay, so we're going to use Pythagorean theorem to do these problems. So this is what one would look like. I will give you either the height or the slant height, and I might give you the radius. I could also give you the diameter. If I give you the diameter, remember, this particular measurement would be half of the diameter. Remember, diameters go all the way across. Okay. So we plug in, let's see, I've got my two legs here. Remember, the two legs are attached to the little square. The hypotenuse is always the side that is opposite the right angle. So I don't know C in this case. Okay. So 20 squared and 11 squared, well, at least we have those on our box one. That's 4. Oh, no, we don't have 20. We have 11. So 20 squared is 400. That's an easy one to do in your head. 11 squared is 121. If we add those two together, that would be what, 521, and we do not have that on our box. Number one, everybody understand what I mean box one? That was that box one way back when, the first section of the chapter, and then we wrote in box one the first 16 perfect squares. So we grab our calculators, we take the square root of 521, and I get about 22.8. Okay, if I round that to the nearest whole number, 22.8 is about 23, or to one decimal place, 22.8. Remember, square roots of non-perfect squares are irrational numbers, so I have to put the approximation symbol because it's not exactly 22.8. Those decimals never stop and they never repeat. Any questions? Okay, moving on. 11 and 5, once again, it looks like we have our two legs. So this is just a matter of plugging these numbers in. We're going to be calculating the slant height here. The two legs, remember, are attached to the little right triangle, and the side that is opposite is the hypotenuse, the C value. Okay, so 11 squared plus 5 squared equals C squared. We got this from box one, 121 and 25. We can even do that in our head. 5 plus 1 is 6, 2 plus 2 is 4. So we get 146. That's not in our box. Let's see if we can do this one by hand. Let's see, square root of 146. 146, what are the two perfect squares? Somebody that squeeze 146.
144 and 169.
144 and 169. There we go. 144 and 169. Okay. Square root of 144 from box number one is 12. Square root of 169 is 13. So it's somewhere between 12 and 13. Now, once again, hey, we're only 2 away from 144 to 146, but we are what, 23 away? That's a lot. 23 away from this one. So we are really as close to 12 as you can get without actually being 12, right? I guess the closer you get as a whole number would be 145. Well, that's got to be 12.1. I mean, it's got to be 12.1. You can take your calculators, you can confirm the square root of 146 is in fact 12. Well, mine says 0.8. Well, that would round to 12.1. So hopefully you're understanding that at least for the first 16, it's not that big of a deal to actually do this without a calculator, right? So you can do this without a calculator, at least as long as the numbers are small. So about 12.1. All right, so here's our first one that's a slight challenge. Remember, this would be a challenge because side opposite the right angle is C. So we have B and C. We're missing the A value. In other words, we're missing the height of this particular cone. Well, it's no big deal. We're still going to use the Pythagorean theorem to set this one up. So A squared plus B squared equals C squared. A is the unknown right here. C is 6. I'm sorry. B is 6 and C is 11. Let's just do some math here. 6 squared is 36. 11 squared is 121. Now we use a little bit of algebra to get to the answer. Get rid of positive 36 by subtracting 36 from both sides. 121 minus 36 is 80. What is it? 85. And now we take the square root. For those of you that are comfortable with this estimation process, you can almost do this in your head. I mean, the first perfect square that's smaller than 85 is 81, and the next one is 100. So you're not super close to 81, but you're close. So I don't know if I had to take a guess, maybe 9.2, right? 9.2 would probably be a good guess, and ends up being 9.2 is the answer, okay? I left off the decimal. So be ready for either rounding to the nearest whole number, or rounding to the nearest tenth. Just read the instructions and see what it says. All right, any questions so far? So we did pyramids, square pyramids. We did cones. The only one of the cone one we haven't worked is if I give you a diameter. So I don't have an example for that one today, but just be ready for it. I'll give you a diameter. In other words, I'll give you one that goes all the way across. And this diameter right here, if that radius was 6, the diameter would be 12. So if you're not careful, I'll throw one in there, and then you'll throw 12 into the formula instead of 6. So just be ready for that. And there will be one tonight for homework like that. All right, so I wanted to make sure that we had the most time to do the most challenging ones. And the most challenging ones are, what is the diagonal distance of a rectangular prism? So basically, you got a box. What's the longest object you can fit inside of a box? And that would fit diagonally from the upper, let's say, right corner to the lower left corner, or vice versa. Okay, that would be the largest object. So we start off with a box, rectangular prism. And we say, what's the largest object in there? So if you remember from Monday, the process, it's a little complicated. It requires you to do the Pythagorean theorem 2 times, and I'll slow down. Okay, I would absolutely encourage you to rewatch the video. I'll have it posted well before 8 o'clock tonight. So it'll get posted somewhere probably before 3 is my goal. So I'll have it posted by 3 p.m. I'm going to make it today. Have it posted by 3 p.m. So that big red line right there, that is what we're looking for. What is the longest object that can fit inside this box? That would be called the diagonal distance. Notice I'm going from the upper left to the lower right. That's the longest object that will fit inside this box. I could also go from the upper right to lower left, okay? So how is this done? Well, we're going to make a right triangle. And the right triangle that we're going to make would include that side. And, well, that's not a side, that's a diagonal distance along the bottom rectangle of the box. So that the black, I'll make it green here. This one right here, that is, oops. This one right here, that is the diagonal distance along the bottom square, or rectangle in this case, from the upper left to the lower right. This one is not something that's typically measured, nor is the red one. So that is ultimately the triangle that I need to calculate for in order to find out the red. Remember, red is what we're really looking for. But in order to do that, well, I need this bottom diagonal line right here. This one, this black one right here, well, this one will be given. That's the height of the prism, right? But this diagonal right here, this one isn't typically given to you. So that's the one that we're going to calculate first. And then once that's done, we'll have this side and this side of the right triangle. Remember, this is a right triangle. Then we can calculate the red one, which is ultimately our goal. If that doesn't make sense to you, make sure you replay the video slowly, bit by bit, until it does. All right, let's do this calculation. So here's a real one, right? So I have a rectangular prism. We're going to calculate the diagonal distance of this box. In other words, what's the largest object that can fit inside? In order to do that, now we're going to get into steps. Step number 1, on the bottom rectangle, draw that diagonal. For those of you that your eyeballs are flipping around on you, it's like, oh, the box is changing on me. I feel for you. That happens to me as well too. But find the bottom rectangle and draw that diagonal right there. Notice we now can calculate that diagonal dotted line. Why? Because this is really a right triangle right here, side length 3, side length 4. And for those of you really on the board, hey, it's a 3, 4, 5 triangle. If you didn't realize that, then throw the numbers in the Pythagorean theorem. Remember, the side opposite the right angle is the hypotenuse. In this case, our dotted black line right there. All right, so 4 squared is 16, 3 squared is 9, 9 plus 16 is 25, and the square root of 25 is 5. So we just figured out that this black dashed line right here is the length 5, okay? So let me put that, I'm gonna erase all these calculations. Remember, you can rewatch the video, slower speed if necessary, rewind it. So we just found out that that dashed line right there is 5. Now we draw, so there's a whole big one, step 1, okay? Remember, our ultimate goal is the red line right there. Now, I'll make it outlined in green here. Now we can figure out our triangle a little bit easier, or at least visually see it. So our triangle is the dotted line, the red line, and the black line. That is ultimately what we're going to use, and it's a right triangle. That is ultimately what we're going to use to calculate the length of the red line there, okay? So the red line is the diagonal distance between the top left of the box to the bottom right of the box, okay? All right, well, let's do that. Remember, the side that is opposite the right angle is C, and that in this case is the red line. So we got leg lengths of 3 and 5. So 3 and 5 are what go into my Pythagorean theorem. 3 squared is 9. 5 squared is 25. 9 plus 25 is 34. So the answer to this one, what's the longest thing that we can put in there, is whatever the square root of 34 is. Well, once again, I mean, I can almost squeeze this in our heads, right? The two perfect squares that squeeze 34 are 25 and 36. 34 is really close to 36. Square root of 36 is 6, so a little bit smaller than 6 would be 5.9, or maybe 5.8 would be good guesses. For those of you with your calculators in your hand that just did it, you find out it's 5.8. Okay, so 5.8, I'll round it to 6. So 6 would be the largest units, inches, centimeters, whatever it is, would be the largest thing that can fit inside this box. Now I did round, it's really 5.8, but I do want you to notice that the box has a height of 3, a width of 4, and a length of 3. So you got a box that's 3, 4, 3. You would not think that something that's 6 inches, if it was measured in inches, long would fit inside this box, and it turns out it can if you fit it diagonally. All right, any questions? So you've seen this now 3 times, right? So let's do one together. Let's do one together. All right, so there's our box. Our box has dimensions of the length of 8, a width of 10, and a height of 10. And I believe, I forget who guessed it on Monday, said, oh, we're guessing like something 12 inches would fit inside this. That was our guess, and we found out we were really wrong. I mean, we were off by a significant factor. So the calculations, it's basically 2 steps. Step number 1 is to, along the bottom rectangle, draw a diagonal line. You don't have to make it dotted, but I made mine dotted. That line that you just drew forms a right triangle. And the dotted line is your C value, and 8 and 10 are the 2 legs of that right triangle. Stop me if I'm going too fast. So 10 and 8 are my A and B, and I do the Pythagorean theorem to find the distance of the dotted line. That's 100, that's 64. 100 plus 64 is 164. I look at my box number 1, that would be 169, is a little bit larger. And 144. Well, it's really close to 169, but not super close. So 5.9, 5.8 would be the right measurement. Why did I say 5? I have no idea where I got 5 from. I'm sorry. 164 is 69 is 13 squares, so it's a little bit less than 13. I have no idea why I said 5. And that would be 12.8-ish, right? 12.9 or 12.8 would be good guesses. If I wanted to leave that as a whole number, then I would round up to 13, okay? Be careful if you're doing this in real life, obviously when you're rounding, right? And we're rounding up in this case, then the error that you're introducing in this problem is on the plus side, meaning that it truly isn't a 13-inch object that will fit diagonally on the bottom. It would be something close to 13 inches. All right, so let's see. Okay, so we just found out that the distance along the bottom diagonally is now about 13. So about 13. So to complete our triangle, we use that number, this number, and then we draw our final answer, which is that red solid line right there. That is the diagonal distance between the upper left, lower right. Now, if you had drawn this black dotted line from this corner to this corner, all right, and then then you'd go from that corner down to this corner. And it can, I'm sorry, from that corner down to this corner. And it can work that way as well too. It's the same distance, by the way. All right, remember we just made a second right triangle. There's the right angle, and the red solid line is opposite the right angle, so therefore it is the hypotenuse. So it's side length or legs 10 and legs 13, right? 10 squared is 100. 13 squared is 169. We get what, 269 here. 256 is 16 squared, so it's bigger than 16. I don't have a good feel for where it is because I don't know the next perfect square off the top of my head. Maybe you do. 17 squared, right? Turns out that 17 squared is 289. So it's a good distance away from 289, but it's also not really close to 256. So I don't know, maybe we're guessing 16.4, 16.3, something like that. And it turns out that 269, the square root of that is 16.4, okay? Now notice this time I'm rounding down on this one. If I round it up on the 13, then actually I'll be pretty darn close to it. Remember, our initial guess from Monday was that a 12-inch object would fit in there, and it turns out that a 16-inch or centimeters, whatever we're measuring it, object will actually fit in there as long as it's skinny, right? But yeah, that's the basic idea. I will say that the kids that get this, they get it very well. It's not that complicated a procedure, but I do have some students that struggle mightily at this. For those students, I would recommend watching this video as you're doing your homework. Like, play it one step at a time. Don't don't become so overwhelmed by the entire problem. Play it maybe one sentence at a time or one step at a time, and then you do the step on yours. I mean, the only difference is that your numbers won't be 10, 10, 13, and 8. You'll have different numbers, but the procedure is exactly the same. And yes, as mathematicians, we are lazy when we don't put the word units. We should always put the word units. All right, does anybody have any questions? Questions? I got Abby, Amber, Callie, Donovan, Jace, Jackson, Prudence, and somebody called Reconnecting, which I'm sure is someone, but don't know what their name is. All right, anyone with a question? Okay. All right, well, believe it or not, that actually does it for today. Now, it was a complete reteaching of the previous lesson, not because we needed a reteaching necessarily, but because you need 2 days of this for this to really lock into your brain. It is just an application of Pythagorean theorem. For those of you that did poorly, I called your name out there on the quiz. Hopefully you're getting better at the Pythagorean theorem, becoming more comfortable with it. As a warning to you guys, we're going to be using Pythagorean theorem for the rest of the chapter. And if I go way back to the calendar, that's a lot of slides. If we go way back to the calendar, we can see we have no quizzes or tests before spring break, but every one of these lessons right here uses the Pythagorean theorem, okay? If there are no questions, let's see, what we got? 15 minutes left of class. So let's use, I'm gonna leave the video on. Let's use those 15 minutes to open up your worksheet, look it over, and I'll leave the video on. So if there's any questions, you can ask me questions. In fact, I'll pull up the, I will pull up the worksheet and we will take a look at it together. Pythagorean theorem in 3D number 2. Pythagorean theorem in 3D number 2. There we go. All right, so we have cone, 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 pyramid, 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 and then box, box, box. So a whole lot of practice on these. All right. Now, as this says, find the slant height. So basically what we're missing here is the C value. Be careful on this one. Look, I'm giving you the diameter, not the radius. Then find the height. Remember, the height would be the, oh, I didn't share the document. Sorry. You're like, what is he talking about? Share screen. There, that's better. All right, so on these two, we're finding the slant height of each. So no big deal. Remember, this would be your C value right here. Notice here, I have the diameter. So you have to change that to a radius. That didn't work. Find the height of each cone. So what I'm asking you to do is, remember, the height is the perpendicular distance between the base and the vertex. So you got a right triangle. I'm giving you the C, I'm giving you B. So what we're missing here is the A value. Over here, the same thing. The height would be like that. That's what we're solving for. And over here, I'm giving you the diameter. Make sure you use the radius in your calculations. All right, what else we got here? Okay, pyramids. Slant height, remember, is the distance along the outside. So for question number 3, remember the slant height would be this distance right here in green. There's your right triangle right there. Nothing really tricky for those. What else? Find the slant height for here. I'm sorry, find the height. I was going to say the slant height is right here. So finding the height of this, question number 4, remember, that would be the perpendicular distance between the vertex and the center of the base. That would form a right triangle right there. So this would be your C value. 6 would be, remember, we got to take half of that. That would be 3. I can't write 3 small enough. Oh yeah, I can. There, look at that. So that would be 3. So you're solving for A here, and you can do that for these as well too. And then last but not least, our favorite, the box. And then we're finding what is the longest diagonal of each prism. In other words, what is the longest object that will fit inside the box? So for the second one right here, that would go from here down to here. Remember, though, in actuality, step number 1 is along the bottom is to draw that diagonal. So that's actually step 1. Draw that one. And then what you're really finding, once you find that green part, is this one right here. Red is the, oh, that's a horrible line, but you get the idea. Can I draw that better? Oh yeah, there's a straight line here. Now it's going to be perfect. Boom, look at that. Okay, and how are you going to do that? Well, you're going to find the distance of green first. It's hard to see it. It's hard to see it, but in actuality, this right here, because it's a rectangle, it's actually a square in this case. Or no, it's a rectangle, 12 and 9. That is a right angle. So that side is 9, this side is 12. Where did I get the 12 from? Because right here, that side would be the same as this side, which would be the same as this side. So it is 12. So we got a rectangle of 9 and 12. Those are your A and B. Plug it in to find what that green line is right there. Whatever that is. Then we got one leg of 9. The aforementioned, whatever the green one is, that'll be your B value. Do the Pythagorean theorem to find out what the red line is. And boom, you're done. And so am I. So unless you have any questions, get started on your worksheet. I'll have my computer on. Like I said, if I'm not in class, I can answer chats. If I'm in class, you're going to have to wait until the end of class, that sort of thing. But yeah, that's what we got going on. And then we will meet again tomorrow, same time, same bat channel. And we'll do more Pythagorean theorem stuff. Anyone, any final questions? Final questions? I have one question in the chat. Okay, got it. Got you, Jace. Sounds good. All right, I'll catch you guys tomorrow. Have a wonderful day and be safe out there.